The concept may be far-fetched, and the reality may be very different than this. But the idea itself is not so crazy. Physicists have been thinking about tunnels in time too, but we covered it from a different angle. We wonder if portals to the past or the future could ever be possible within the laws of nature. As it turns out, we think they are.
You just have to change your perspective and get down to the tiniest of scales, to the level of atoms and the particles inside them.
You might find it a tough concept, but stay with me. Nothing is flat or solid. If you look closely enough at anything, you'll find holes and wrinkles in it. It's a basic physical principle, and it even applies to time. Even something as smooth as a pool ball has tiny crevices, wrinkles, and voids. Now, it's easy to show that this is true in the first 3 dimensions. But trust me, it's also true of the 4th dimension as well. There are tiny crevices, wrinkles, and voids in time. Down at the smallest of scales. Smaller even than molecules, smaller than atoms. We get to a place called the quantum foam.
Down at the quantum level, the laws that govern this tiny realm appear completely different from the familiar laws that govern big, everyday objects. And once you catch a glimpse of them, you never look at the world in quite the same way. It's almost impossible to picture how weird things can get down at the smallest of scales. But what if you could visit a place like this, where the quantum laws were obvious, where people and objects behaved like tiny atoms and particles? You'd be in for quite a show. Here, objects do things that seem crazy. I mean, in the quantum world, there's a sense in which things don't like to be tied down to just one location, or to follow just one path. It's almost as if things were in more than one place at a time. And what I do here can have an immediate effect somewhere else, even if there's no one there. And in experiment after experiment, the quantum laws have always been right.
It's the best theory we have.
There are literally billions of pieces of confirming evidence for quantum mechanics.
It has passed so many tests of so many bizarre predictions.
There's no disagreement between quantum mechanics in any experiment that's ever been done.
But in 1935, Einstein thought he'd finally found the Achilles heel of quantum mechanics. Something so strange, so counter to all logical views of the universe, he thought it held the key to proving the theory was incomplete. It's called entanglement.
The most bizarre, the most absurd, the most crazy, the most ridiculous prediction that quantum mechanics makes is entanglement.
Entanglement is a theoretical prediction that comes from the equations of quantum mechanics. 2 particles can become entangled if they're close together and their properties become linked. Remarkably, quantum mechanics says that even if you separated those particles, sending them in opposite directions, they could remain entangled, inextricably connected. It's kind of like this wheel. When it stops turning, it will randomly land on either red or blue. Now imagine a second wheel. If these two wheels behave like two entangled electrons, then every time one landed red, the other is guaranteed to land on blue. If you measured a particle here, not only would you affect it, but your measurement would also affect its entangled partner, no matter how distant.
Quantum computers require a totally different architecture and a totally different way of programming. When you program a computer, you're basically telling one CPU, the Pentium chip, how to process information. So you have a CPU with inputs and outputs, and then you have a software that controls the CPU. That's called a Turing machine. But quantum computers are not. Quantum computers compute on individual atoms. And instead of zeros and ones, which are called bits, we have quantum bits or qubits. That is sometimes 1, sometimes 0, sometimes any number in between 0 and 1. That's the source of the power of quantum computers. The fact that you're no longer calculating on zeros and ones. But the problem with quantum computers is precisely because you are no longer computing on zeros and ones, how do you program this thing? It's very difficult. The way we do it today is with an MRI machine. We get a bunch of atoms, line them up, put them in a magnetic field, shoot electromagnetic radiation at it from an MRI machine, flip the charges, so 1 becomes 0, becomes a half, becomes 2/3, and then we measure the echo. That's how we do it today. And then you begin to realize how difficult it is to make quantum computers. The problem is interference. Cosmic rays, a rumbling truck outside your door, small tremors in the earth, they create vibrations sufficient to destroy the spin of the electron. And that's the problem. That's the reason why we don't have quantum computers.
So you need to create a very quiet, clean, cold environment for these chips to work in. And ultimately what we're building is a quantum computer on a chip that's about the size of your fingernail in this very exotic environment. So that environment runs at near absolute zero. So absolute zero, as you know, is the lowest temperature possible in the universe, so-called 0 degrees Kelvin. So these machines run at a very low temperature so that they can have that pristine, very clean, quiet environment to run in, and it doesn't disturb that quantum computation.